Okay, hello everyone. So today we're going to tackle torque and moments, and in particular, we're going to deal with the calculations that are associated with torque and moments that deal with equilibrium. Okay, so before everything, let's have a quick review. So when we talk about moments, like in this very famous meme that came from Avengers Infinity War, when something is perfectly balanced, as all things should be, from the very finger. So we have this stick and it's balanced by one finger at its very center. Okay, this is what you call a pivot point. This is where it is supported, okay, and this is where the center of gravity is roughly located. This is where the support is, right? And we apply a force at one side of this pivot point, and it is some distance away from the pivot or support. This will result in what you call a moment, which is equal to F times T. If you don't know what F times T is, F is equal to force, and D is equal to your distance. And because force is a vector quantity, we would also say that moment is a vector quantity. And it can be clockwise or counterclockwise. So for example, this moment over here, okay, we can see that this goes down and it's at the right side. Therefore, it is a counterclockwise kind of moment. Okay, by convention, clockwise is said to be the negative and counterclockwise the positive. Okay, now when we talk about principle of moments and when we're trying to balance everything out, rotational equilibrium is reached when the sum of clockwise moments and counterclockwise moments is equal to zero. So this is just a way to word this very simple equation, which is the sum of moments is equal to zero. Okay, so when clockwise and counterclockwise are equal, then that means that we have rotational equilibrium. And when you're going to design buildings or structures, okay, let's say you want to design this bridge and it's supported only on this side, okay, now you're going to put a person here. He's going to therefore have a bit of a moment. You want everything to be perfectly balanced. You need to be able to calculate, okay, how much support must I put here such that it will be balanced? Because if it's not balanced, then you're just going to have this guy go down and it's going to be like a diving board. But I don't think you want that in a bridge, don't you? Okay, so we want to solve for rotational equilibrium in moment problems. Now, here are some example problems. Let's start with a simple one. Okay, so let's say we have a 200 Newton child that is seated at an unknown distance from the pivot point, and he or she, I can't really tell, is balanced out by this 400 Newton child seated 1.5 meters away from the pivot point. Now, from inspection, they are not the same mass, they are not the same weight. However, there is a way to still achieve rotational equilibrium, and that is if their moments are equal. Okay, so this girl, I'll just call this the girl. Okay, this girl exerts a counterclockwise moment. This one, as you could see, would exert a clockwise moment. And by the equation, we know that the sum of all moments must equal zero. That means that the counterclockwise moments plus the clockwise moments must add up to zero, or they are essentially equal. And if we look at it, okay, which is the counterclockwise moment? Well, we have this girl over here who has a 200 Newton force or weight, and we actually don't know the distance, so let's just label that D. Now, how about the clockwise moment? Well, we have this boy over here who is seated 1.5 meters and 400 newtons. Okay, seated 1.5 meters away from the support and 400 newtons of weight. And we know that to be negative, okay, because it's clockwise. So we have 1.5 meters times 400 newtons, okay? And we know all of that to be equal to zero. Now, I think you can rearrange this simply in order to get D, and that will be 400 times 1.5, and you can put that to the other side, divided by 200 newtons should get you the distance required. Okay, now let's go and grab my calculator real quick. I'll just keep these annotations as said. Okay, so that would be 400 times 1.5 divided by 200 gives me a moment of 3, or rather a distance of 3. So when we go back to this slide, okay, if this girl is seated 3 meters away from the center of support, then they should balance out, and that makes a bit of sense. Okay, if you want a heavier object, if you have a heavier object, you want them to be closer to the center of support. Okay, and that will mean that closer to the support means less moment. So 3 meters is the final answer for this problem. So this is a simple example of the pivot point being exactly at the center of gravity of the moment arm, or this seesaw. Now, what if we have this kind of example wherein, yes, your pivot point is there, but it's not at the center of the seesaw, as you can see. So you still have two objects. Okay, you have this cat, or two cats. This is the orange cat, at a position 0.5 meters from this. Let's just say this is a ruler. Okay, 0, and we know this to be 2 meters long. Okay, so this cat over here is seated at 0.5 meters, at the 0.5 meter mark. Okay, this cat over here is seated at the 1.75 meter mark. Let's just make it 0.50 to be consistent. Now, in this case, you would typically solve for the moments of both cats, but there's one thing that you have to account for. When the pivot point, as you could see, is not at the exact center of the seesaw, it's not at the center of mass of the seesaw, then you have to also account for the fact that the seesaw itself has its own mass. And therefore, if it has its own mass, then it will also exert a moment. And according to this, the force of this seesaw, the weight of this seesaw is 30 newtons. Okay, so we know this to be at the position 1.0 because that's the exact center. Okay, and it exerts a force downward of 30 newtons. Okay, let's just clean up my drawing a little bit. So 0.50 meter mark, and you don't know the mass, or you don't know the weight rather. I should relabel that. F of 1. Okay, as for this one, you know that this guy is 70 newtons, and he is at 1.75 meters away from the pivot point. Okay, so in this case, when we get to the moment equation, the sum of all moments is equal to 0. We have to account for the clockwise and counterclockwise moments. And how many counterclockwise moments do we have? We have 2, because this is one of them, the cat, and the other one is given by your seesaw. Okay, because if the cats were to leave, this seesaw would tip in the favor of the counterclockwise direction because it is off center. So we have to account for that, and we have to say that the moment of cat 1 plus the moment of the seesaw, okay, is the counterclockwise moments. Now, how about this one? The clockwise moments would be this cat number 2. Okay, and what are their moments equal to? So one thing is, you're given positions here. Okay, if you want to get the distance from the center of support, then the important thing is you have to subtract. Okay, so you know that the pivot point is at the 1.25 meter mark. You know that this cat is at the 0.50 meter mark. Therefore, this distance over here would be 1.25 minus 0.50. Okay, and this would be equal to 0.75 meters. So this cat is 0.75 meters away from the center, not 0.50, but 0.75. Now, how about the ruler or the seesaw? So this seesaw over here, the center of gravity is at the 1 meter mark, the center of the actual seesaw, and its center of support is 1.25. So therefore, this distance over here is 0.25 meters when you subtract. So that's the moment arm. Now, when we talk about this cat over here, 1.25 meter mark is the center of support, and it's seated at the 1.75 meter mark. Therefore, this distance over here is 1.75 minus 1.25, which is 0.50 meters. So there, you have the actual distances now. We can now calculate for the missing quantity, which is the how much weight does this cat have. So let's see, cat number 1. Well, you don't know the weight, so let me just label that. You don't know the F of this cat, but you know that this cat is positioned 0.75 meters away from the center of support. Now, let's account for the seesaw. The seesaw itself has a force or a weight of 30 newtons exerted at a distance of 0.25 meters away from the center of support. And finally, you have cat number 2. Okay, negative because it's clockwise, sorry. So this cat over here, 17 Newton force exerted a distance of 0.50 meters. Okay, so when we run our calculations here, so we can put everything to one side. So it's just going to be 30 newtons times 0.25 minus 70 times 0.50. So when we subtract that, we divide that by 0.75. So let me get my calculator real quick. Calculator. Okay. Clear. Oops, I accidentally discarded everything actually. Now, what was that again? 30, I apologize, times 0.25. Okay, this is really weird. Okay, and you know that there's a negative moment minus, okay, let me just try to remember it. Calm down. 70 times, okay, 1.75 minus 1.25 is 0.5. So this will be equal to that. And we know we will divide this. When we transplant this to the other side, it will be just 27.5. So we simply divide this by, make this positive and divide this by the distance of this thing from the center. So what's 1.25 minus 0.50? That's 0.75. And we will get, okay, 36.6 newtons. However, we have to also account for the fact that this would be positive. So the final answer for this problem would be force 1 is 36.6 newtons. Okay, so this cat over here, 36.6 newtons. There's a ruler or the seesaw that has a 30 Newton force at the very center. And you have cat number 2, 70 newtons. So I hope this simple exercise was enlightening for you. And eventually, when we get to the more complicated examples and the practical examples of this topic, we're going to look more into these off-center center of gravities, okay, wherein the pivot point doesn't really match where the center of gravity of the object is located. So thank you for watching. I hope this was useful for you. And please take care, and I'll see you when we get back from our Christmas break.